So in this module, we're going to look at some example problems that are related to the content that we covered in Module 1 of this lecture. And one thing that I wanted to bring up is even though these aren't just going to be example problems related to the content in Module 1, I'm actually going to use a couple examples in order to introduce some new concepts. So first example problem, we're given a binary number, 1100, 1011. We know it is in binary due to the subscript of 2 and the fact that all the digits are either 0 or 1, making it a valid binary number. First and foremost, we're asked to clarify how many bits, nibbles, and bytes are in the binary number. And then we want to convert that binary number to decimal, assuming that it is in unsigned binary, as we discussed in the actual first module. So you'll notice that I provided the scans of the actual solution here, but here is the binary number that we were given. Remember that number of bits is just a term for how many digits there are in the binary number. So all that I want to do is count the digits in any particular order. It's always a good habit to start at the least significant bit or the bit that is worth the least. And just like in the decimal number system, that's going to be the digit that's all the way to the rightmost digit in the number. So here is the first bit, second bit, third bit, fourth bit, and of course keep counting and you will find that there are 8 bits total. If you notice when I wrote that binary number, and I believe when it was typed on the slides, I actually split the number into sections of 4 bits. So for those of you that are familiar with how a social security number is written with those dashes after the first 3 digits and kind of that before the last 3 as well, remember that what those dashes are doing is they're kind of organizing the number to make it easily interpretable when you look at it visually. And when we write numbers in binary, we do the same thing. Particularly, we'll take groups of 4 bits and kind of write them with a little bit of space in between. And that's because 4 bits is 1 nibble. So if I want to convert and if I want to determine how many nibbles are in this binary number, I can multiply the 8 bits by a conversion factor that relates the number of nibbles to the number of bits. 1 nibble is 4 bits. When I place that 4 bits in the denominator, the bits cancel, leaves me with something in units of nibbles, and 8 times 1/4 is just 2. And using a similar approach, we can find that this 8-bit number is 1 byte. So make sure that you're familiar. Those are just things that you have to commit to memory, particularly for those of you that are going to be working in computing fields. They're incredibly important to know the relationship between bits, nibbles, and bytes. The second question asked us to convert that to decimal, assuming that the encoding is what is known as an unsigned binary number. Now, don't worry about that too much because we only have 8 weeks and because this is a computing focus course for engineers, we're not going to talk about the other methods of encoding like 2's complement to encode negative numbers and so on. But just note that this conversion that I'm doing here is assuming something about the underlying meaning of each of those bits. Particularly, we're assuming that the only thing we're encoding are unsigned decimal numbers, which is a fancy way to say positive numbers. And when we do that conversion, what we want to do is a place value expansion like we looked at in the first module of the lecture. So I'm just going to take starting all the way at the rightmost bit. Remember that is called the least significant bit or LSB. I will take the digit, which is 1, and I will weight it by its place value. And all the place values in binary are going to be the base of 2 raised to a particular power. It's going to start at 0 in the least significant bit. And as we move 1 place to the left, it's going to increase by a factor of 2. So this bit 1 is in the 2 to the 0s or the 1's place. The next bit immediately to the left is in the 2 to the 1st place. So that digit will weight by 2 to the 1st. We don't have 1 here. If we did, that would be in the 2's to the 2nd or 4th place. In a similar fashion, you can just keep multiplying by 2, 1's place, 2's place, 4's place, 8's place, 16's place, 32, 64, and 128. So you notice since the only bits that are on are the bit in the 2 to the 7th or the 128th place, 2 to the 6th or 64th place, 2 to the 3rd or 8th place, 2 to the 1st or 2nd place, and 2 to the 0th or 1 place. Really, to do that conversion, I'm just adding up 128 plus 64 plus 8 plus 2 plus 1. And if you do that, you will get 203, and that is the equivalent decimal number there. So example 2 is going to introduce a little bit of a new concept. And if you ever look at actual assembly level or kind of machine code, oftentimes when you have it's just a bunch of binary numbers. But when you look at it in an actual file, you'll see a bunch of mix of numbers and actual letters. And that is a number system that's known as hexadecimal. And you can view hexadecimal as a number system that's intended to basically compress binary numbers into a more compact form when you write them. And when you look at the actual name of the number system, hexadecimal, it's probably not hard to understand that that's going to be a base 16 number system, meaning that the place values of all of your digits is going to be 16 to an increasing power, and that you're going to have 16 digits available from 0 up to 15. But if you think about trying to represent numbers that are greater than 10, kind of between 10 and 15, as a single digit, we're not going to be able to do that using our traditional base 10 number system because we only have 10 digits there. So what people have decided is that to encode anything that would traditionally take two digits, like 10, 11, 12, 13, 14, and 15, we're going to use letters. So that's why the digits in the hexadecimal number system go all the way from 0 to 9. So we use the 10 that we have in the decimal system, and then they're going to go A, B, C, D, E, F, where A encodes 10, B encodes 11, C encodes 12, D encodes 13, and E encodes 14, and F encodes 15. So what we were asked to do is to convert this binary number from the prior example, 1100, 1011 to hexadecimal. So what you're going to find is that since hexadecimal is intentionally designed in order to kind of compress or write binary in a smaller or shorter format, the conversion process is really easy. Basically, what you want to do is just grab each nibble individually, convert it to decimal, and then convert that decimal value to a corresponding digit in hexadecimal. And it doesn't matter which order you do it. You just have to preserve the order, of course. So I can start with this nibble all the way over to the right. And I'm just going to look like this at this nibble as if it were in isolation. So the binary number 1011, what would that convert to in decimal? Well, remember, if you're just looking at the nibble in isolation, this is 1, 2, 4, 8. So you have 8, you have 2, you have 1. So that is 11. Now move over to the next nibble and ignore the fact that it is kind of placed to the left in place value. Just take it in isolation. What would it convert to in decimal? Well, 0011, remember again, 1, 2, 4, 8. So 8 plus 4 will be 12. And if you think about those kind of digits in hexadecimal that we spoke of earlier, remember that you start using letters when you get to 10. So A is 10, 11 is B, and 12 is C. So what we've done there is we've taken each nibble, we've converted it to decimal, and then we've mapped the decimal values to the corresponding hexadecimal digit. So this nibble corresponds to 11 in base 10, which is B in hexadecimal. This nibble corresponds to 12 in base 10, which is C in hexadecimal. So this binary number, 1100, 1011, is just going to convert to CB in hexadecimal. So you see immediately why I called this a shorthand for binary, because you can basically take 4 bits or a nibble and replace it by a single digit in hexadecimal. So oftentimes when you have a binary file, which is just a bunch of ones and zeros, you will see it not necessarily represented in binary, but represented in something that looks like numbers and letters. But note that those letters will only be between A and F. And that is the reason why it's actually in hexadecimal. So let's look at the next problem here, where we're going to be asked to, given a Boolean function, draw a gate level schematic corresponding to the function. Remember, the reason that we're doing this is that in computing, all of both the arithmetic, kind of the underlying ALU within a microprocessor, along with the memory, is implemented using these kind of gate level devices, which under the hood are actually transistors, but their mathematics is described by Boolean algebra. So we want to be comfortable with the idea of working with Boolean algebra. So given this function, f equals quantity a plus b times c, we want to draw a gate level schematic corresponding to the function. We want to evaluate it for particular values of the input. And then we want to classify it as either being a combinational or sequential digital circuit. And we want to specify why. And we'll talk about why that is important in a minute. It actually is not went over in the first module of the lecture. It's one of those new things that I wanted to go over with you. So when you look at this function, whether it's an actual Boolean algebra function or standard algebra function, the meaning of parentheses is withheld. Particularly when operation is in parentheses, we're using that notation to force someone to recognize that it needs to be done first. So when I interpret quantity a plus b times c, I know that I need to take the binary variables a and b and place them in a plus operation first. So the question is, what is the actual plus operation? Well, as we discussed a little bit in the actual initial Module 1 lecture, and as we'll get to practice a little bit in this week's lab, you can kind of look at the digital cheat sheet that I posted in your module for this week as well, or actually it's in the week 1 module. The plus operation in binary corresponds to the Boolean algebra operation of an OR or an OR gate. So all that we need to do is know that we need to take these two inputs, A and B, and we need to put them into whatever piece of hardware would implement the Boolean plus, which is an OR. And from that cheat sheet, we know that a Boolean OR gate is drawn like this. It has this curved side on the left side for the input. The two inputs A and B go in, and out of that gate, it will produce A plus B. Now, what do we need to do with that output A plus B? Well, we need to take that output signal, which will also be a binary, and we need to multiply it with the input C. Well, what actual gate has the capability of implementing multiplication? Well, if you go back to that truth table, you'll see that multiplication in Boolean algebra corresponds to an AND gate. So what I need to do is find the schematic of an AND gate, which will have a pure vertical line on the input side and then a rounded side on the output side. What goes into the AND gate? Well, one of the things that will go in is C. So I have C going in here. And the other thing that goes in is the output of that OR gate. So I'm going to take the output of the OR gate and I will wire it to the input of the AND gate. And if I put these two signals, A plus B and C, into an AND gate, the output will be whatever the first signal was, which is expressed in terms of the input variables, quantity A plus B, times C. Now, if you want to actually clarify or kind of classify rather this sort of digital circuit, you would say that it's a two-stage circuit because the inputs A and B are fed through not one but two stages of gates. And another thing you want to notice is the output isn't fed back to the input. And that is what makes it a combinational logic gate. And if you learn anything, for those of you that are going the ECE route, you're going to see this electrical or computer engineering. You're going to see this in a lot more detail. But for those of you that are not, it's still important to know that when you think about computing devices, they're all implemented using this kind of gate level logic, and they fall into two bins. One bin takes the input and it just puts them through a bunch of gates sequentially, and it eventually generates an output. And if there's no feedback, if that output never comes back to the input, that is called a combinational logic circuit. And all of the underlying circuits that have the capability to do math are implemented using that combinational logic architecture. The second that the output comes back to the input, that's what actually gives it the capability to have memory. So all of your memory circuits are implemented with feedback. And those are called sequential logic circuits, not combinational logic circuits. So just make sure that you're familiar with those two terms, particularly if a digital circuit, if the output doesn't come back to the input, it's combinational, it's used for arithmetic. If it does, it's sequential and it is used for memory implementations. So let's actually look at the last example problem here, which is going to be useful as we start to get into our coding examples this week. Technically, this is wrapping up week 1, but in week 2. So assume that we are writing software for an embedded computing device. So this is a really cheap computer like a microcontroller or a Raspberry Pi or an Arduino, whatever term you might be familiar with. And say we're actually trying to implement a night light. I'm not sure if any of you have these around your house, but think about the cheap things that you plug into a wall and you want them to turn on when there's no ambient light around, so no other lights are on. And in addition, someone's actually in the proximity. You don't want them to just be on forever. So in order to do that, this device would need two sensors, a photo sensor, which is going to detect whether or not we have ambient light in the surrounding, and a motion sensor, which is going to detect whether anyone is within the range of our actual night light. And we're going to assume that those two sensor outputs are encoded. So somehow there's hardware that makes the output of those sensors be represented in the software as either a 1 or a 0. And we're going to call those variables light and motion. So this is really getting ahead of ourselves, but we're kind of thinking of what's coming through the rest of the semester. Assume that you have access to these variables light and motion, and they are binary variables, either a 1 or 0. And if light is 1, what that means is there's light in our surroundings. And if light is 0, that means there's no light in our surroundings. And similar idea for encoding motion. If motion is 1, there's motion in the surroundings. If it's 0, there isn't. So what we want to do is actually write a Boolean logic statement that can be used to generate a control signal. And we'll call this variable control to turn the light on and off. And let's assume that the control signal should be 1 when the night light should be illuminated and 0 when it's not. And then let's start to ask ourselves, are those names of the variables we picked, light, motion, and control, good variable names? And why or why not are they good variable names? So going to the solutions here that I posted, here we are. So if we look at the problem description and kind of knowing how this nightlight works, we want the nightlight to be illuminated when there's no ambient light in the surrounding, which means that, again, if we're encoding light as 0 means no light, light 1 means light, light would be 0. And then when there is a human in the proximity, which again, if we're encoding motion as 1 and not motion as 0, that would be motion is equal to 1. So we are going to want to generate the actual control signal to illuminate or kind of drive the light to be on whenever the light is 0 and whenever the motion is 1. So how would I actually write a Boolean algebra expression in order to do that? Well, since we need two things to be simultaneously true, we're going to use an AND type operation. Versus if it could be one or the other, maybe something like the control of the dome light within your car, where you want that to be on if any of your doors are open, that would be an OR. But here we need both things simultaneously to be true, so we're going to use an AND gate for implementation. And what do we want the inputs to be? Well, we want this control to be 1, meaning turn the light on, when motion is 1, and when light is 0. So hopefully everyone can see that's why I took the light variable and I put an inversion operation on it. Because when light is 0, that means there's no light, we want to turn it on. The not of that would be 1. And when motion is 1, we want to turn it on, and 1 would give me a 1. In any other situation, right, that control signal will be 0. It will only be 1 when light is 0 and motion is 1. And that'll kind of take a little bit of time to wrap your head around, but basically that's something that would go in the actual control block of some type of conditional code statement within your embedded system, as we'll see when we get a little bit later on in the course. But hopefully that made sense. And for this last module, I'm actually going to use an older video just because I'm a little behind with the course just getting set up a little bit late. But if you have any questions on it or any of the videos, feel free to reach out, and we'll get started with the week 2 modules on Wednesdays like usual.